Today we're moving on to chapter 3. We've been looking at data that is categorical. Here we're looking at quantitative data instead. And this is something that you have more experience with already, at least if you've been at Northland for any length of time, because the junior high textbooks that we use do some of this stuff. In fact, a couple of my examples are straight out of my 7th grade pre-algebra class. Okay, so with quantitative variables, there's no, when you say intrinsic here, I would ask him to add that to his list. Does he know what intrinsic means? To make piles of data, the way we did with categorical. Right, with categorical, if it's in this category, we put it in this pile, and if it's in this category, we put it in that pile. Usually what we'll do is divide up all possible values into what are called equal width bins, then count the number of cases that fall into each bin. This is called a histogram. So, for example, this particular bin, the distance for the bullseye is 3. It could be equal to 3, or the distance could be greater than 3, or less than halfway between 3 and 6 is 4.5, or less than 4.5. It does not include 4.5. If it was exactly 4.5, that would go into the next larger bin. So you include the bottom but not the top. That's something that comes up sometimes. And it's something actually that, for my 7th graders, I test them on that, and it takes them a little while, but they usually get it eventually. So notice that unlike a bar chart, in a histogram, there's no spaces between the bars unless there's a gap in the data. So with a bar chart, there's a bar between them because there was no reason to shove them together. Each one is independent of everything else. But here we shove all these together because, well, why would you have these gaps unless there is an actual gap in the data? So almost always this is going to be counts. Very rarely, but occasionally, if we replace the counts over here with percentages, we get what's called a relative frequency histogram. Yes?
Is it between 3 and 5?
4.5.
Oh, okay, sorry.
No, I didn't make the 5 ran into my decimal point. Yeah, so greater than or equal to 3, but less than 4.5. Okay? So now if we don't change the bin width, the shape of a relative frequency histogram will be the same as this one. It's just that the numbers over here will be different. So it'll basically look like the same shape. Just like we saw with categorical data when we did bar charts. If we changed it from counts to relative frequency, it looked exactly the same when we had percentages instead of counts over here on the vertical axis. So, yes? Yeah. What's halfway between 3 and 6? So it's 4.5. It's just the midpoint of those two. Okay? No, don't be, not a big deal. All right. So if you have forgotten or never learned, tonight's assignment, you'll learn how to create a histogram. One of the things that comes up is, well, how big do I make the bins? And that's always a good question, and there is no hard and fast answer for that. Okay? What I will say is you want to have, you know, some bins. If you end up with a histogram that only has 2 bins, it's really not going to tell you anything. But if you overdo it, you have 30 bins, well, that may be too much depending on your data. Now, with some data, 30 bins is the right way to do it. It just depends. It's more art form than it is, a hard and fast science. And when you do these with your calculator, which you'll learn to do as well, the calculator will pick the bin width for you. Now, does it always pick a bin width that I like? No. Sometimes I'm like, I don't like that bin width, and you can go in and change it. Okay? That's true for the 84, and it's also true, it's the only thing that I don't like about for those of you who are getting the NumWorks calculator, occasionally it picks stupid bin widths. And I'm not sure why. I've actually spoken to representatives a couple of times and have been like, hey, what's the deal? And they've assured me that they're looking into it. Don't know if that means that it's gotten fixed yet. I need to email my guy and say, hey, what's going on with this? All right. So another one that is, again, straight out of the 7th grade textbook is a stem and leaf display or a stem and leaf plot. Your book calls it a display, I call it a plot. Doesn't matter. It's like a histogram, but it has the advantage of keeping the original data values. You don't lump everybody together where you don't know where they all piled up over here and only one of them's over here or something like that. Maybe he hit the bullseye 10 times and then once it was over here. We don't know that from this. Yeah.
So with the histogram, you're kind of clump numbers together.
You're putting them into groups.
Okay.
So it'd be a little bit like, if in a class you're like, everybody made an A, everybody made a B, everybody made a C. You're putting them into groups. Okay? The groups that doesn't have to be the same number of people in them or the same number in each, but the width of each group has to be the same. Okay? So, according to your book, stem and leaf displays are especially useful when you make them by hand for batches of fewer than a few hundred data values. This cracks me up. A few hundred? Are you nuts? They say, do it by hand for a few hundred. I'm like, no. Now, you may be given a stem and leaf plot that has 100 in them, but making one that has 100 or so by hand, oh, saints preserve us. No, thank you. I do not want to spend my time doing that. So here's another example taken from pre-algebra with the weight of each girl on a basketball team. And it has this. The unfortunate part about this is it may be that you're like, I don't really know exactly what this means. There should always be, when you do a stem and leaf plot, or you're given one, a key that tells you what's going on. So on this, for example, I would need to have something like this, 11/2 like that, which would be this entry. means 112 pounds. Right? You need to know how we're reading this, and you also need to know what the units are. So that tells you both of those things. This particular one, you'll also notice that the smaller numbers are at the top and the bigger numbers at the bottom. And that feels a little bit weird. Sometimes you'll see them done the other way. It just depends. When I make them myself, just because I'm so used to the y-axis, larger values on top, I almost always do them that way. But the nice thing about doing them this way is if you take your paper and rotate it to the left 90 degrees, and you have a histogram. And it's the way that you would normally read it, smaller numbers on the left, larger numbers on the right. So that's an advantage to doing it this way. And then you can make, comments about this particular distribution. So in some ways, a stem and leaf plot is a 2-for-1. It gives you all the original data, and it also gives you a histogram. And we're going to be really interested in how data is distributed. One of the things that will be on the AP exam, guaranteed 100%, is that someplace they'll give you something that is either a stem and leaf plot or some other kind of plot, and they'll ask you to analyze how the data is distributed for whatever it is. Okay, and we're going to talk a lot about that on page 2 in just a second. So a dot plot, which we've done before in class, just places a dot along an axis for each case in the data. So like a stem and leaf plot, dot plots preserve the original data values, but they don't group the data into bins. So on this one, this would be all of the vehicles that got 30 miles to the gallon. And this is all of the vehicles that got 31 miles to the gallon, right? This is useful only if you don't have a great big spread in your data where you would need to have lots and lots and lots and lots and lots of dot things. Like the one that we did on that first day, where it was how many of these did you get right? Well, the possibilities were from 0 to 12. That worked really nicely, and it was always a whole number. So this is why dot plots get used less than some other things, because it's got to be a whole number, and if it's a huge spread of data, it doesn't work very well. Okay? So again, before you draw, if it's a histogram, a stem and leaf display, or a box plot, that should be dot plot. Sorry, I was thinking about what was on the back. A dot plot, check that the data are values of a quantitative variable whose units are known. All right, let's go on to page 2. So when you talk about a distribution, there are 3 things that you should talk about. Actually, there's more than that, but these 3 are the basic 3, and then the other ones are if they come up. So you should talk about its shape, its center, and its spread, or how variable it is. So let's look at shape. So does the histogram have a single hump or several separated humps? High spots, if you will. Spikes. Those humps are called modes. A histogram with one peak is called unimodal. This stands out above its neighbors. So this is unimodal. This, we've got a mode over here and another mode over here. This is bimodal. Can you think of a time of any kind of a situation where you think you might get bimodal data? What kind of a thing might you be measuring, and upon whom might you be measuring it that would give you bimodal data?
Cars that come to school.
What now?
Pick up and then drop off.
Oh, so times when there are a lot of cars coming through the school? Yeah, that would be bimodal. Absolutely. What if you were measuring the heights of a group of adults? Why do you think that might be bimodal? You both started at the same time. And go. Pardon? Yeah, there would probably be, a spike, at the middle of where men are, and then a spike at the middle of where women are. Then they aren't typically the same height. Okay, as a group. Okay, that might be bimodal. We occasionally see bimodal data, and most of the time when we see bimodal data, you actually go, oh, if there's a way to separate this, I probably want to separate it and look at the males, look at the females, and do your analysis separately rather than together. Okay? Multimodal, we almost never see it, and it almost always makes us go, ick. Right? What am I supposed to do with this? It's hard to draw any conclusions from it. That, and if on this one you happen to have made the bins twice as wide as they are, if you made the bins twice as wide as they are, it would almost be flat across the top, except for where this one is, and you would have one peak and then the rest of it would be kind of flat, and that's not particularly interesting either, other than to note it looks like you're flipping somebody off. All right? So a histogram that doesn't appear to have any obvious mode, where all the bars are about, and again, this is part of the statistics is way more relaxed than any other math class is. Are they about the same? Yeah, they're about the same. Okay, that's called uniform. Uniform doesn't mean perfectly aligned across the top. There's some variation, but we say that is uniform. All right, next, still talking about the shape, is it symmetric? Now, symmetric doesn't mean perfectly symmetric, right? If you were to, well, this is kind of disgusting, but if you were to take a person and you were to cut them in half from the top of their head all the way down, the two halves are not quite the same, okay? At the very least, your liver and gallbladder are on one side, and there's nothing corresponding to that on the other side. That and no one is perfectly symmetric. Okay? But we still say that humans have what's called bilateral symmetry. The left side and the right side they're pretty close to the same. So this diagram shows something that is both unimodal and symmetric. The left side and the right side are about the same. Notice they're far from perfectly the same, but it's close enough. Okay? You can have bimodal and symmetric or multimodal and symmetric, but it's less common. Occasionally you'll have something where you have almost the same peak on both sides and then going down from there on both, and it's like those two look almost exactly the same. And again, think about if you fold it in half in the middle of the graph, do the two halves kind of match up with each other? So then sometimes when it's not symmetric, we'll have this where the ends of the distribution on the left and the right are called the tails. If one tail stretches out further than the other, the histogram is said to be skewed to the side of the longer tail. I used to get this confused all the time, frankly, before I started teaching statistics. I thought that where the peak was what told you which way it was skewed. But it's the other way around. It's where the tail is. The tail tells you, that's difficult to say, which direction the skew is. This is right skewed. And this is left skewed. Okay? I don't know why I thought it was the other way around. I thought it for years. So, again, this picture right out of the 7th grade book. This one is symmetric. I would also say it's somewhat bimodal, right? This is skewed, and I would say it's unimodal. This one is single peaked. That's what the 7th grade book called it. We would say unimodal. On that one in the middle, let's talk about symmetry just real quickly. It's not quite symmetric, is it? But is it strongly skewed? Not real strongly. I mean, this is crazy strong skew, right? It may be slightly skewed to the left, and we'll say things like that. Not just that it is slightly skewed, we might say it may be slightly skewed. We hedge our bets all the time with the language that we use in statistics. And then this one, although not perfectly level across the top, is uniform. This double peaked, again, we would call that bimodal. And this is an example of one that's bimodal and I would say symmetric as well. Right, the left side and the right side look alike. If we were to draw a line down through the middle, the two halves, and you folded it, right, the left and the right would look alike. All right. Let's do a little bit of this page so that we can finish up the shape. Are there any unusual features? Does something stand out to you? So you should always mention any potential outliers. Later on, we'll talk about how to calculate outliers. There's actually two different ways that I know of, at least. I think there are others to calculate outliers. Again, if you were here, for pre-algebra, you learned one way to do it. We'll learn another way to do it as well, and we'll use both. Just depends on what kind of data we have. So when we're describing it, we'll usually say there appears to be, or there is a potential outlier here if we haven't actually done any calculation. Or it looks like there's an outlier because, man, that's a big gap between those. Now, an outlier can be an informative part of your data, or it could be something went wrong. Someone put the decimal in the wrong place, or something like that. You never just throw them out. Okay? Although we're pretty loosey-goosey about everything, throwing out data is not allowed. Unless you can either verify that it's an error, or you're like, I feel that this outlier is problematic. Let's look at the data with the outlier and then look at the data without the outlier and see if that changes things greatly. So when you have an outlier, there's always going to be a gap. But just because there's a gap doesn't mean that this is an outlier. Right? So if there's a gap, but you don't think it's an outlier, just note, there's a gap in age between 80 and 90. There is nobody in the 80 to 90 group. Here, I would probably say there's a likely outlier, because I'm pretty convinced that this really is an outlier, in the bin that goes from whatever to whatever. I'd have to look at this more to figure out exactly. Maybe I'd say in the bin centered at 64.8. Okay? All right. Let's go ahead and talk about median. We'll get through that. You guys, you already know about median. You've been doing this since, I don't know, 6th grade, maybe earlier. So the middle value that divides the histogram into 2 equal areas is called the median. The median has the same units as the data. In middle school, you probably learned to find the median by first ordering the data from least to greatest, and then picking out the middle number if it was odd, or averaging the 2 that are together if it was even. You should get to the place where you can look at a histogram and fairly quickly find the median. So for this one, there's 2 in this bin, plus 4 makes 6, plus 4 makes 10, plus 5 makes 15, plus 3 makes 18, 19, 20. There are 20 values. So I'm going to find, well, where is the 10th value? Because my median is going to be between the 10th and the 11th. Since there's an even number, it'll be between 10 and 11. Okay? So let's see, 2, 6, 10. So it looks like the median is probably about 50. Because if we put it here, there are 10 in this bin, and there are 10 in these, or there are 10 in these 3 bins, and then there are 10 in those 4 bins. There's an equal number of data points both above and below that point. Sometimes these are easier than others. On the AP exam, frequently, and you've got a calculator to help you, there's bins, there's 20 bins, and they're the sizes are large sometimes, and you have to go, okay, I have 500 people in this, I need to find where is it 250 about. Okay, questions about that? Sorry, you looked like you were about to ask something. Okay. Your eyes shifted.